these travels and consultations and everything else, I remember Nangandiriku in 2016, I was working for the IMF on a project in Moscow in Russia. So I was doing, I was asked to do the tax architecture for the Russian government. So I also do financial stuff on the side. So when I was there for like six months. And the thing that strikes you is people respect you as much as the level of development of the background that you come from, right? So no matter how good you are, if you come from a very messed up background, people always ask you, but why aren't you fixing your that's the question that everyone will ask me. Why aren't you fixing your own environment, right? You're coming here to do our tax system, but what about what about Zim, right? What have you done for Zim? You know, so all those questions always come up, and this is why, even if you look at someone like Professor Arthur Mutambara, you know, we always have very heated arguments. The thing is, it doesn't matter that you've taught at MIT and so on, but the fact that you haven't managed to influence and do and contribute to some significant change within your own country, you will never gain any respect, because people will say, he's brilliant, but look where he comes from, right? So you never get any respect, right? So this is why you tend to find that when you travel overseas, people will respect you because of where you come from, right? So if you're American, people automatically assume you are good at what you do, right? And if you're African, they actually assume you're third best, right? And you actually have to prove yourself that you're actually better than everyone else. Yeah. So the realization is we need to fix our own environment, and no one else will fix the environment for us. So that's part of the reason why I came back home, right? Because I actually don't need to be here, right? But also take it this way, you guys are benefiting. Like, this is volunteer work, right?
Yes, Doc.
Yeah, true, Doc.
Yeah, so why are you complaining?
We are not complaining.
You want me to be somewhere else.
Thank you very much for the volunteer work.
Yeah, so I think this is the thing. No one will fix Zimbabwe for us except ourselves, right? So there's no foreign direct investment that's going to come from individuals that will sort out our economics. It has to be us who fix things. If we don't realize that, nothing will ever change. This expectation that someone will come with a big bag of money from overseas and will say, "Here you are, Mr. Njuling, sort out your economy." It's not going to happen, right? It's going to be you guys, creating innovations that will change this nation for the better.
Thank you so much, Doc. I think this is what you're doing is also part of solving our own Zimbabwe. Thank you so much. We appreciate that.
Now, all right, guys. So I think we're enough now. We can start. So can you please download the? I shared the CSV file for Pima Indians. If you can all please download it. And what we'll do is we'll write the code from scratch. So the expectation now is everyone should open up a blank Jupyter notebook, and we'll start coding from scratch. Yeah, you know, that question I get asked a lot. Even my own mother never thought I'd come back, but I'm here. Like everyone else, I'm here. Right?
Do you have other investments out of the country? Like
Of course. I've got investments out of the country, and also obviously in Zim.
that's great.
Yeah, that's a given, right?
Hello, Doc.
Yes.
I don't know if it's me only, but I'm failing to download that database. I'm getting that dataset. I'm getting a message. Let me just go back again. Couldn't preview the file. You may be offline or with limited connectivity. Try downloading instead, but there's no option for downloading. I don't know if it's me only.
Oh, okay. Let me show you how you download. Let me share my screen.
Thank you.
All right, let me share my screen. Yeah, so can you see my screen?
Yes.
Yeah, so what you do is you click on the file like this. So you see it comes up with this, right? So you don't want to preview the document. So what you do is you come here where there's the printer icon, and then you say open in a new window. Yeah, can you see this? Yes, guys. It says can you? It says open in a new window. When I click open in a new window, it then opens a file, and then it says here download. Can you see this? Then if I say download, it will then download the file. There you go. It's downloaded. Yeah, that's easy enough. Yeah. Yes, that's easy enough.
Yes, I've seen it.
So what I can do is as well is let my full screen. How do you upload a file on Google Meet, on this Google Meet? Time captions, settings. I can't see where you. But anyway, I've shown you how to download. So please download the file So we can start. Have you imported the file?
Yes, Doc.
Yes,
Yeah.
Doc.
All right. Okay. All right. So let's do this. So let's start. So what we're going to do is we're going to do. Well, yeah. All right, guys. So what we want to do now is we want to so from our data set. So if we open our data set. Right, you notice that our data set. Can you see it's a CSV file? You will notice that this data set does not have any headers, right? Yeah.
Yes, Doc.
It doesn't have any headers, so what we're going to do is we're going to use the information that we've been given to say the data set includes data from 68 women with 8 characteristics, in particular number of times pregnant. So what we need to be able to do is we need to now create labels for our data set, right? So that when we import the data into pandas, we're able to identify each column. Right? Yes? So what we need to do is we need to import pandas as PD. We import NumPy as NP. We import matplotlib.pyplot as PLT. And then from sklearn.model selection import train test splits. So this function is what, or library, this is what then splits our data into training set and test set. And then we import TensorFlow, and then we import Sequential, and then we also import a dense.
Excuse me, Doc.
Yes.
Sorry, Doc.
Yes.
Is this file shared with anyone, or we are just writing from our end from scratch?
Well, we want to do this from scratch, right? So that you actually so that you're not just opening a Jupyter notebook, and we want everyone to type from scratch.
Okay, thank you.
Right, so we import this, yes, and then if we run it, so I can probably assist by copying some of the code, so everyone understands why we're doing this. So remember, from yesterday, we remember yesterday what we said, right? So from yesterday we and we said that so every neuron. So remember, we said every neuron connects to every other neuron in the next. Connects to every other neuron, right? And then we said we call this a dense architecture, right? Yes. Yes.
Yes.
Yes. Yes, sir.
Yeah. Remember, guys, we said we call it a dense architecture. Yeah. Is this clear?
Okay.
Yeah, guys, you said it right. And then we also said that the number of neurons in each hidden layer, right, is we define the number of neurons for each hidden layer and also the activation function for each hidden layer. And then what we also said that since the information is flowing in a forward direction, we said these are called feed-forward neural networks, and the when we're building these models, we're adding each hidden layer sequentially, right? Because we're adding one hidden layer after the other. So therefore, we then said, right, so what we're doing is we're building dense sequential models, right? Yes, guys?
Yes, Doc.
Yes, Doc.
Yeah, and that's understood. So then if you look at when we're importing TensorFlow, so this from Keras, so we're using what is called the Keras API. So what we're saying is we're importing so that we create a sequential model, right? And that sequential model that we're building is dense. By dense, we meaning every neuron connects to every other neuron in the next layer, right? That's straightforward to understand, yes? Why we've included these two?
Yes, Doc. Hi, Doc. I think
Yes.
so that we don't trail behind, if you can also help with pasting the codes in the chat box.
Okay, all right. Where is this? There you go.
Thank you.
I should speed up things, right? And then, so what we want to do is we want to create headers for our data. So how we do that is we create a list. If you will recall, when we did pandas, right? We said pandas, we've got a series, and then you've got a data frame, and then you've got a panel. So what we want to do is we want to import our data frame so that we have headers for our features, right? So that we're able to identify this is number of times pregnant. So what we do is we create a list of these, right? So we say, for example, features is equal to, we create a list, and then we then assign that list to the data that we're importing, right? So the first one is a number of times pregnant, right? Yeah, according to this. Yes?
Yes, Doc.
So we can just call it pregas for short, right? Yeah?
Oh, okay.
Pregas, not chief.
It's too ghetto.
Leslie,
It's too ghetto. Because
I'm not, that's what he's saying. Number of times pregnant, so they will just call it pregas for short. Right? Does anyone have any better suggestion? All the ladies are quiet. This was Roga. This was
all right.
And then the second one is glucose. Yeah, the plasma glucose concentration, right? So we can just call it plasma, right? And then the third one is diastolic blood pressure. So we can just call it BP for blood pressure. Yes. And the fourth one is triceps skin fold. So we can just call this a skin fold. And then the fifth one is 2-hour serum insulin. So we can just call it insulin. And then the sixth one is body mass index. So we can call it BMI for short. And then the seventh one is diabetes pedigree function. So we can call it diabetes pedigree. We call it
sugar.
Okay, yeah, all right, sugar. Okay, and then we've got age, right? And then we've got the class, whether it's the diabetic or not, right? Yeah. So we can run this, right? So I can copy and paste this into. Right, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, that's 8, that's 9, right? So what we then do is, let me copy this and put it in the, well, I've already copied that into thing. So what we want to do next is we want to we want to read the data, right? So if we call that data and then we say pd.read CSV, and then if we say the names or the labels are equal to features, so what that will do is it will then read the data. Then if we say data.head, you'll see it is assigned pregas, plasma, BP, skin fold, insulin, BMI, sugar, age, and then class, right? So you can then copy this and then I'll paste it into the chat. Right. This is clear so far, yeah?
Yes.
Yes, so far so good.
Right. So the first thing that we want to do is we want to do some exploratory data analysis. So what we'll do is we want to find the shape, right? We want to find the shape. So we've got 668 rows and 9 features, which is exactly the same here. It tells us we've got 68, right? And then plus 9 features, which is correct. And then we want the data.info tells us that the data type, right? It tells us whether there are any missing values within any of the rows and columns of the data. So in this instance, it says there's nothing missing. But it says none now, it means there's no missing data. Then it tells us the different data types of each column or feature, right? And then the next thing that we'd like to do, obviously, is to start doing EDA. So I'll copy this to make it easier for you guys, but data. This you're supposed to be able to do it on your. Right, and then we do some EDA, right? So by EDA, we want to just plot histograms and look at the distribution of the data. So I do a data.hist, and then I want the fixed size to be 10 by 10. That is the plot of each histogram output, right? So I can see for pregas, plasma, BP, skin fold, insulin, body mass index, sugar, age, and class. So you can see I've got 2 distinct classes, 0 and 1. Yeah, this is clear, yes?
So far, so good.
Yes.
Yeah, and then what we want to do, right, based on this, what we want to do in this instance is we've got this is our data, right? So what we want to do is we want to assign right? We want to predict the class. So this is what we're trying to predict, right? Right. So what we're trying to do is we're trying to right? We're trying to predict the class. So this is our Y, right? Are we in agreement? Right? And everything here is our X. Yeah?
Yes, Doc.
Yeah, that is clear, yes?
Yes, it is.
Yeah. So what we want to do is we want to be able to select the values of so we want to assign our X by selecting all these values up to here, right? And then we want to select our Y. So we did number pandas. This is where we splice our data, right? Right. So what we want to do is we want to create. We want to assign X equal to all the features from precursor to age. That's what we want to assign to X. But also when we're assigning X, right, we want to select only the values, right? So how we do that is we can say splicing the data is not difficult, isn't it? Because we know that we're starting here at 0, and then we are ending here at is it 9, right? So remember, so what we do is we then say, when we're selecting, remember we do
Sorry,
select
Doc.
all rows and columns. Sorry?
Is it 9 or 7?
Not 8.
So 1, 2.
It should be 8.
It should be 8, right?
4, 5, 6, 7. This is 8, right? And this is 9.
9.
Yeah? That's correct, yeah?
Yes.
So what that means is, remember, this, when we're splicing and dicing, what does this mean? This means select all rows and columns, isn't it? Yes?
Yes.
Yes, Doc.
And then we can then further splice all the rows and columns that we've selected so that we restrict that to so that we assign this to X, right? Right. So that we then just take from precursor to age. So therefore we need then to specify something here, right? So that we've got our correct splicing and dicing of data. So now the question to you now is, what do we put in here, right? So that we splice our data accordingly. So we want to select everything from precursor to age, and we want to leave out
Hello, Doc.
Yes.
So I think it depends on the function that we are using. If you are using log, we can just on the second columns, we can just put edge in at the upper as the upper limit in quotes.
Yeah. All right. That's yeah. So what I did is this. Yeah. So what I did is actually this, where we're saying where we're saying the upper value is 8, right? Exactly as you're saying, is 8. So we select all the rows and all the columns, but then the upper bound is 8, and then we're selecting only the values because we want to leave out. We want to leave out the headers. Yeah. Is that making sense?
Yes.
Right. Because we actually want to select the we want to select the values. So this is what I've done. So everyone has understood how we arrived at this expression, at this one, at this expression, which is this. So dot values means just give us the values and leave out the headers, right? So it will leave out the headers. So when I run it, it then looks, X looks like this. It's now a NumPy array just with the values, right? Yeah? Yes?
Yes, Doc.
Yeah, so that's easy enough, isn't it? Yeah. So I can copy and paste that into. And now for Y, you can either, since it's just one, the one way to do it, the lazy way to do it is to say Y is equal to, you then say data, right? And then you put quotes and then class and dot values, right? So this is the lazy man's way, right? That's the easy way to do it. Or you can also use ilog, yeah? Yes? You can also say Y is equal to what in terms of ilog? So it's then data dot ilog yeah, and how do we only select the and here is dot values. So what animal do we put in here so that we only select Y?
-1.
You put -1.
All right, so I say well, what I just put a -1. Well, what's the correct way of doing it?
Colon -1.
All right, let's see. Let's see.
I
Let's see.
put something in the chat, Doc.
Sorry.
I've put something in the chat for that expression.
Okay, let me go to the chat. All right. So that's X. So one way, the way you've done it is you've said Y. Yeah, but you see this. This gives you the right? So let's so remember you need to say dot values because we only want the other values, right? So then if we then say Y, then we'll see whether we get, yeah, so this is correct, yeah? Yes, guys, that's correct, yes, isn't it, right? So here we, yeah, so this is correct, yes?
Yes, Doc.
Yes, Doc.
Yeah, so the next thing that we then need to do is we've selected our X and we've selected our Y, and the next thing we need to do is we need to split our data set into training set and test set, isn't it? Yeah. So because we've if we come up here, we're using this function from sklearn dot model underscore selection import train test a split, right? So let me let me copy that into yeah. So so remember when we did a feature engineering, right? So if we examine our data, right? If we examine our data, we can see plasma is 6. So the Pegas is 6. Plasma is 148. BP is 142. Skinfold is 35, and body mass index is 33.6. And then here we've got insulin being 168 and 453 and so on. So one thing you'll discover, you've got varying ranges of values, right? Yeah. Can you see this? We've got different scales of values. So when part of what we do in feature engineering is when you've got for machine learning models, right? When you've got varying range of variable values, you want to scale. You want to scale. You want to scale the features, right? So that they're within the same range. right? So there are quite a number of techniques that are used to scale features so that they are within the same range. So one of the techniques is mean max scaling. Right? And the other one is standardized Z scaling. Right? So with min max scaling, all you're simply doing is the new value of x, right? If we call it x, is equal to x, right, minus x minimum divided by x maximum minus x minimum. Right? And then standardize its scaling. So what this will simply do is, if I take the value of x in a particular column, subtract it to the minimum value, and then I divide that to x max minus x min. So what that would do, it will squash all the values so that they're between 0 and 1. Yeah. So therefore, it will give me any values if you use this formula, right? So for example, if we look at our data set, so what that will mean is if I take I look at what is the minimum value of x in this column, right? So therefore, if I want to substitute 6, therefore I then say 6 minus, I think 0 is the minimum, yeah? Here in this column, right? Minus 0 divided by the maximum value minus the minimum. Let's say in this instance, I can only see 10, right? So therefore, we replace 6 by 0.6. Then we move on to 1, right? And then we then say 1 minus the minimum is 0 divided by the maximum 10 minus the minimum 0, which is equal to 1 over 10, which will give me 0.1. Yeah, and then we then replace this one by 0.1 and this one by 0.6. So what that will do is all of these values, corresponding values, will all be squashed to values with all within the same range. Is that clear? So all of these values will all be within the same range, right? So if we look at this one, for instance, let's say the maximum value is 183. So therefore, we then say, we look at what is the minimum value in this instance. So it then becomes 148 minus, let's say the minimum value is 78, divided by the maximum value, let's say it's 183, minus the minimum value, which is 78, which will give us some value which is about 0.7. Therefore, we replace this by 0.7. Are we together? So that all your values are all now squashed between, right? Is that clear, guys?
Yes.
Yeah.
Yes.
So what you will find is when we do exploratory data analysis here, right? We've got, for example, if you look at plasma, it's the skewness of plasma insulin. Insulin has got a maximum of about 500, right? And then it's got about a minimum of almost a 0, body mass index 250. All of these have got varying range of values. So what that will do is when we are doing our gradient, descent, it means that the when you've got varying degrees of values, varying range of values, it will take a very long time to converge. So when they're all within the same range, it converges faster. Yeah, that is clear. Yes.
Yes,
so,
Joe.
Yeah. So min-max scaling, that's simple to understand. Then standardized scaling is also straightforward. So standardized scaling, we replace x is equal to xi minus the mean divided by the variance, right? So we replace, so this is standardized scaling. So this is just a normalization of data. Yeah, that is clear, yes?
Yes.
Right? Yeah. Yeah. So what's, you know how to calculate mu and you know how to calculate sigma, isn't it? Yes? Come on, guys. Right? So what that will mean is if we're now using that formula, we for example, we take 35, let me say 35 minus the mean, right, mu, divided by the variance sigma, right? And that will give us our Z, standardized Z scaling. Right. So what that will do is it will normalize the data. So if we now go to the code, here we standardize. We're scaling the data using mean max scaling. Yeah. So we scale our data using, so there's a function from sklearn dot pre-processing import min max scaler. Right. So what that will do is I import the min max scaler function, right? And then I create, so what I'm scaling in this instance, if I come back here, what I'm scaling is my x, right? Are we together? What I'm scaling is my x. And then the question is, why am I not scaling y? Come on, guys, why am I not scaling y?
Can I try? Because if it's an output, it will just be standardized according to how X has been scaled.
Yeah, because this is a class. If you look at this, is 1 and 0. So even if I use min-max scaling, right? If I say 1 minus 0 divided by 1, it will still give me 1, right? Yeah? Then if I say 0 minus 1 divided by 1, it will still give me 0, yes? Come on, guys, using min-max scaling.
Yes.
Yes.
Yeah, so it's not going to change anything, right? So therefore, I'm only going to scale my x. So therefore, if I say scaling is
Hi,
equal to
Doc. Sorry,
min-max.
sorry
Yes.
to interrupt. Does it mean that for all data sets we don't have to scale Y, or is it just for this particular one?
For all so we'll look at each one in the, as we do each problem, and then we'll look at do we scale Y or not and the reasons for it. Right? In this instance, it's because it's a class, it's a categorical variable. It doesn't need to be scaled, right? It's either 0 or 1. Yeah.
Okay. Yeah, that's fine. Thank you.
Right. So therefore, we are importing this function min-max scalar, and then we're assigning it to scaling. Therefore, I create a new feature called x scaled, where we're scaling all the values of x, right? And then I say scaling dot fit transform x. So what that means, is I want to transform my x so that it is scaled, right? Using min-max scalar. So therefore, I can then run this, and then I can then look at my x. Can you see now all the range of the values? Yeah, it's all between what 0 and 1, isn't it? Yes.
Hi, Doc. I want to ask, let's say I have my time series data and then I plot it, I see that it's skewed. Can I use this min-max scalar to normalize the data?
Yeah, so let's yes, absolutely. So you can scale as well. You can scale a time series data.
Okay, thank you.
Yeah, absolutely. With time series data, you can also scale it using min-max scalar. Yeah. So after that, what we then do is we then split our data into training set and test set, right? And remember, we said that we need when we were talking, when we were discussing the I remember we spoke about the input input space and output space. Right? Right, that we need to train, split our data so that we are able to train it, right? And then after we train, then we run our learning rule on F test, right? So that we are able to get our predicted values of Y. And then we then compare this to our Y test, right? So that we see how well our learning rule is able to learn the representation of data, and that will then give us our error rate. So therefore, what that means is we need to then split our data into X train, right? X test, Y train, and Y test. And what we then do is we want to dedicate majority of the data to training and a few samples for testing. So therefore, what we do is we say the thumb rule is we say 80% goes to training, and then 20% goes to testing. So you'll see here we then say X train, X test, Y train, Y test. Then I say train test split, right? Then I take my X scale, right? I'm now splitting my X, and I'm also splitting my Y. Then my test size is equal to 0.2, saying my test size is equal to 20% of the data, right? And then random state is equal to 44. What that means is right. So let me paste that, right? So what that means, right? So let's see what that means, right? So well, what we want to avoid in machine learning, right, is what we want to avoid in machine learning is for our machine learning algorithm to learn. What we want it to do, right, is we want it to learn the. Let me bring this down here. Right. What we want it to do is we want it to learn the representation of data. Right. We want it to learn a representation. Representation of data, right? And we want to avoid it learning ordering of data, right? By ordering of data, we're saying the sequence in which the data appears. Right? So to do that, we do something. We want to randomize the values, right, so that they are not predictable in terms of their order. So it's similar to when you're playing a game of cards, makasa. You need to say, if you don't want to make the game predictable, right, you need to say, no chukucha my cards, isn't it? No chukucha, right? And then you then distribute the cards, and then you start playing the game. Otherwise, if you just take the cards as they are, and if you play the game, it becomes predictable. Yes?
Yes, Doc.
Yeah?
Yes.
Yeah, so it's exactly the same principle. So what we're doing here now is we are saying random state is equal to 44, meaning chukucha my cards 44 times so that it becomes random, right? And not predictable. Yeah? Is that making sense?
Yes, yes.
Yes, Doc.
Yeah? Everyone this is clear, yes?
Yes.
Sure, Doc.
Yes, clear, Doc.
Yeah? So then you'll see from here, I've just run it. We want to then see the xtrain.shape. So we want to see the shape of xtrain. You see now we now have, instead of 768, we now have we have 614. So if we say 614 divided by 768, you see it will give us 80%. And then if we say y shape, y test, you see I've got 154. If I say 154 divided by 768, it will give me 20%. Yeah?
Sorry, Doc. Sorry.
Yes?
You explained something where you're saying the xtrain.shape is giving us 614, right? On the number of rows, right? And from the first one, which one, the data.shape, it was giving us 768. What do we call that difference, the 80%, that one which comes out?
Yeah, remember here we're saying we've split our data into training and test set, right?
Mm-hmm.
Yes? And here
Yes.
we're saying, when we say test underscore size is equal to 0.2, what we mean is we're saying we're dedicating, we're splitting the data into a test set and a training set. 20% goes to testing, 80% goes to training the algorithm, right? So if I then say 614 divided by 768, it should give me 80%, right? So if I bring out my calculator here, and if I say 614 divided by 768, yeah, you see, that's 80%, yeah?
Yes.
Right, and then 154 divided by 768, right? This will give me 20%, yeah? Which is the 0.2 here, yes?
Yes.
Yeah?
Yes.
Yes.
Yeah, right, that's clear, yes?
Yes, it's clear now on my side.
Yeah.
Right, yeah. So now so now I can take this, paste it. Then if I want to select just one, if I want to select the number of features in X train, which is just this, right? I say X train dot shape 1, then it should give me 8, right? Yes, that's clear, yes?
Yes, it is.
Yes, Doc.
Yeah, so let's go and represent the architecture of the model so that you guys understand, right? So in this instance, we've got X. So let's draw the model that we're trying to create. We've got X1, X2, X3, X4, X5, right, up to X8, right? So these are our features, right? Yeah.
Yes, Doc.
Right, and this is our input as well to our model. Yeah. Yes. So what we're then trying to do is we're trying to we're trying to say, okay, create the first hidden layer, right? The first hidden layer, let's call it H1. We want this. So X1 will connect to every neuron in this layer, right? So therefore it is what? It is dense, isn't it? Yeah?
Yes.
Yeah? That's easy enough, right? And then the number of our inputs are what? X1 to X8 is what? Is 8, isn't it? So the number of the dimension of the input is 8, right? So input dimension is what? So input dimension is what? Is 8, right? Yes, guys?
Yes,
Doc.
Yes.
That's clear, yes? And then if we then specify the next layer, and then if we specify the next layer, right? H2, right? And this connects to this neuron and it connects to this neuron in the next layer and so on, right? That, because this is a dense architecture, right? So, and for this layer, we also specify the number of neurons, right? of neurons, and we also specify the activation function. Right? And we do the same. And then for the output, right? And in this case of the output, we want to be able to predict a 0 or a 1, right? We want to be able to predict a what? A 0 or 1, which is the class. 0 means is non-diabetic, 1 means is diabetic. So what that means is for our last layer, which is the output layer, which is Y. What we want to do is we want to create we want to specify an activation function. So in this instance, we've got 1 neuron, yeah? And we want to specify an activation function that fires when the threshold of 0 or 1, right? So in this instance, that is a what? What type of activation function? Come on, guys. We've gone in detail.
Sigmoid. The sigmoid.
Sigmoid. Thank you. Sigmoid activation function, right? Thank you. Right. So there you go. So now let's go and develop the model, right? Okay. You'll see it's very easy, right? So let's build the model, right? So in this instance, we call it model. All right. So in this instance, you can see we say we want to create a model which is sequential. Yes? That is clear, yes?
Yes, Doc.
Yeah? So the first, we're creating a model that is sequential. Yeah? And you know what we mean by sequential is we mean that it's in a feed-forward direction, right? Right? Because this is the first hidden layer, and that is the second hidden layer, and we go on to the output, and so on and so on. Yes? Yeah?
Yes, Doc.
Okay, thank you. That is clear for everyone. Okay. So, and then by dense, you understand what that means, right? So what we want to do is we want to create a sequential model where we are adding hidden layers one after the other, right? So we are here, we add, right? We add, and so on, right? One layer after the other, we are adding layers. Is that clear?
Yes, Doc.
Yes, Doc.
Yeah. So this is what this model.add means, right? So in the first instance, I've got 20 neurons, and my input dimension is equal to xtrain.shape1, which is equal to my number of features, right? Or my number of variables, yeah? Because in this instance, I've got 8, right? Input dimensions is what? Is 8, yes?
Mm-hmm. Yes.
Yeah, that is clear, yes?
Yes, Doc.
And what I've done is so in this instance, I've got for the first layer, I've got my input connecting to this. So I've got my input, right, connecting to this layer, isn't it? Right? My input connecting to the first hidden layer, right? So what I'm doing now is I specify the dimension of my number of inputs, and then I specify the number of neurons, right? And then I specify the activation function. So we then said the activation function in this instance, we're using rectified linear unit, right? For example, yeah? Yeah, so you've understood, right? So I specified number of neurons and the activation function. So now that layer is complete. And then I'm going to add the second hidden layer. Yes? And in this second hidden layer, now I don't need to specify the input. I've already dealt with the input. I'm now connecting the first hidden layer to now a second hidden layer. I just need to specify the number of neurons and the activation function. Is that clear?
Mm-hmm.
Yeah. So which is this, right? I'm now saying I need to create a dense architecture with 20 neurons and the activation function is value. Then I create another hidden layer, right? The same, and then I create another hidden layer, and now this is my output layer, this one. And now you understand what this one exactly is doing. It's called one neuron, and the activation function is sigmoid, right? There you go. So what we've done now is we've created our model, right? And then we can run this, right? Right? We've created a model. So we've created a model with 1, 2, 3, 4, 5 hidden layers.
Yes.
Right? And one output. Yeah? This is clear, yes?
Yes, Doc.
Yeah. And then I can print the model summary, right? So you'll see in the model summary, I've got I've got dense, right? Meaning that every neuron connects to every other neuron in the next layer. And in the first instance, I've got 180 parameters, yes? Then I've got 420, 420, 420, 420, and then 21, right? So that we understand where these are coming from, right? If we look at, so if we say what is 8? So let me bring out the calculator. What is 8 by 20?
160.
Yeah. Yes.
Yes,
That's
Doc.
clear. Yes. That is clear. Yes.
Yes.
It's 160. Yeah.
Yes.
Right. So that we understand. So if you recall the architecture of a single neuron, it's like this. The mouse seems to be stuck. All right. So remember, we've got it's like this, right? And we've got an activation function. Sorry, my mouse is getting stuck, right? And we've got an input, right? Let's say x1, and then we've got a bias, right? Yeah.
Yes.
Yeah. So what that means is we are adding we're adding a bias for each neuron, right? You say a bias, a bias, a bias, a bias, a bias. Since we've got 20 neurons, it means we're adding 20 biases, right? So therefore, 20 by 160 will give us what? Come on, guys. 20 plus
180.
1. Huh?
180.
180.
180.
Right? So this is where this 180 is coming from.
Mm-hmm.
Yeah?
Yes, Doc.
Right, thank you. So that's where the 180 is coming from. So then in the next instance, we now have in the next instance we now have we're now dealing with the next layer, this one, right? So we now have 20 neurons, every neuron connecting to every other neuron, right? So what is 20 by 20?
That's 400, Doc.
400.
100.
Right, and then what we need, how many biases do we need to add?
4.
Sorry?
20.
20.
Sorry?
20.
20. 20.
And then we get what? What do we get?
420.
Thank you. So therefore, we have 420, right? So you get where these are coming from, yeah?
Yes.
Doc.
Yeah, so it's not a mystery anymore, right? So we understand the architecture very well. Yeah? In terms of the architecture that we've created, right? So I don't have to explain where this 420 and where is this 21 coming from? Can someone explain on the last layer? Where is this? How did we get to 21?
I think it's the last hidden layer plus the output, which is 1.
Yeah, so the last hidden layer, right? So the last hidden layer is we've got 1 neuron, right? So if we look at the architecture, we've got, in terms of the last hidden layer, here we've got 20 neurons, isn't it?
Mm-hmm.
And then we've got 1 output, right? And these are connecting. Yeah? So 20 by 1 plus what? 1
Plus
bias,
1.
isn't it? Which is equal to?
21.
21. Yeah?
Yes, Doc.
Yeah? So so that's not a mystery, right?
Mm-hmm.
Okay, thank you. Right? So that's not a mystery. So we've understood exactly what we've done with our model.
Sorry, Doc, to take you back a bit.
Yes.
That 20, the number of neurons per each layer. Is it something that we just come up with from our head, or we test it, or to say if we put 20, how is our model performing? Then we adjust, or
Yeah,
there are some.
absolutely. So remember, we spoke we spoke about okay. So we spoke about what we call we spoke about what we call what we call hyperparameters. Right. So an example of hyperparameters, we said number of neurons. right? The activation function. Number of hidden layers. Right? And then optimization function. Right? And the learning rate. And the number of epochs. So all of these parameters are called hyperparameters. Why are they called hyperparameters? Because changing these will affect the accuracy of our model. Accuracy or performance of the model. So there's what we call, so we need then to be able to tweak these so that we get the best performing model. So that process of tweaking those parameters is called hyper parameter tuning, right? So hyperparameter tuning, you can think of it as, right? You guys mafara mangoma, right? So imagine I'm a DJ, right? I'm a DJ engineer, and this is my mixing console, right? The mixing console, the network knobs on the mixing console here, right? And so what I'm doing in the mixing console, right? I'm adjusting. So let's say this is the bass, right? This is the treble, and so on and so on, right? And then kuno the name of speakers, right? Right? And so what the DJ will do, right? I don't quicker to my knobs out, and then he hears the output that comes from the speakers, kuti how well it is, right? And he keeps tuning it, right? And then he hears the response, it could be from the crowd as well. The one who say, isn't it? Right? And then it keeps adjusting these, right? But why not if Lina asks Farah, then they increase the volume. You see the volume is here. Then she starts jumping up and down, yeah? So that's exactly the same. So, right? So therefore you can then think of hyperparameter tuning as these as my knobs, and you are the DJ, you're adjusting those to see how you are pleasing the crowd or improving the performance of your model. Yeah? Is that clear?
A very good example, Doc. Yes, Doc. Very clear, Doc.
Okay, so let's move on, right? So the next thing we do, right? So we create the model, right? I've created the model. So the next thing we need to do is we need to compile our model, right? So by compiling our model, let me copy this and then explain what this means. By compiling our model, well, what we're doing is we have to select an optimization technique, right? Yeah, for our gradient descent, isn't it? Yeah, we need to select an optimization technique, right? And the optimization technique, one that we can use is adaptive. Remember adaptive momentum?
You mean Adam?
Yeah, or Adam for short. Yeah.
Okay, top.
Yeah, and what we also want to do is we want to train our model for accuracy, right? And then we also want to specify our loss function, right? We want to specify our loss function because we are dealing with a sigmoid function, right? We're dealing with a sigmoid function, right? Which fires when we either have a 1 or 0. So this means it's what? It's binary. Yes?
Yes, doc.
Yeah? So it means it's binary. But what we want to also do is we want to, when we are dealing with our values, we also want to deal with the uncertainty within the data. So that uncertainty within the data is called a cross-entropy, or people just call it entropy, right? Is this clear? Right? So for our loss function, well, what we're doing is we want to see y hat minus y for binary values, whilst at the same time we want to deal with the uncertainty within the values, and that uncertainty within the values we call it cross entropy. So for our loss function, we select specifically for classification where we put a 0 or 1. So in this instance, we call it a binary cross entropy.
Sorry, Doc. Just a question. When you say you want also to deal with the uncertainties within the data, what example of those will be?
So when we're dealing with with entropy, by entropy we mean in terms of data is we want to deal with the lack of order or predictability, right? Right. So what we want to do, remember what we did with our when we're splitting our data. Takachukucha the data.
Yes.
Right. So therefore, kantachukucha data yatuna, we also want to measure the level of the lack of order, right?
Okay. Okay.
Right. By uncertainty, we mean, to be specific, we're saying lack of order.
All right. That's clear. Thank you, Doc.
Yeah. Lack of order or lack of predictability. This mouse predictability, right? Or lack of, remember I spoke about we don't want it to memorize the ordering of the data. Yeah? Yeah, so this is clear, yes? What we mean by binary cross-entropy for our loss function.
Yeah, it's now clear.
Yeah, okay. So let's proceed, right? So when we're compiling our model, we then specify our loss function as binary cross-entropy, right? And then our optimizer as adaptive momentum or ADA. And then what the metric that we want to measure is we want to measure accuracy, right? That's clear, yes?
Yes, Doc.
Clear, Doc.
Right? So now let's go and fit the model. By fitting the model, we mean we are now training the model. Right? So by training the model, we want to train our model using our X train and our Y train. And that is clear, yeah? Because we're training the model. Yeah? Guys, that's clear, yes? When we're training the model, we use X train and Y train, yeah? Yes?
Yes,
And then we
yes,
also
Doc.
say, sorry? And then what we're also saying is we want the number of epochs. Remember we said epochs. We understand what epochs means. Epochs is the number of iterations that it goes through the data, right? So we want to say when you're training this neural network, go through 500 iterations and then stop, right? And you know what batch size is, right? We went into detail what batch size is, yes? Yes, come on guys, batch size, everyone understands what we mean by batch size. Because we're using what? Stochastic, a variant, Adam is a variant of stochastic gradient descent because we don't want our model to be trapped in the local minima, yes? We want it to always find the global minima. Yes, and therefore we then split our data and specify a batch size, right? Yes, guys?
Yes, Doc, it's clear.
Yes, Doc.
Yes, Doc.
Right? So and then the other thing that you need to understand is by what we call validation split, right? So let's talk about validation split, right? So that we understand, right? So remember we said where was it? Right? Yes. So here we said we split our data into X train, Y train, Y test, and X test. Right? So when you dedicate 80% of the data for training, so what that means is you can only test how well the model is performing when at the end, when you've got Y hat minus Y test, isn't it? Right? But what I can also do is at every iteration step, right? Because I've specified 500 epochs. From step iteration 1 to 500, what I can do is I can split my training data into a small little set, which I then at every iteration step, I actually test to see how well my model is performing. So what that means is I now validate y hat minus y to see how different they are at every single step, instead of doing it right at the end after I finished the training. So I take another little data set. So that data set is called a validation set. Yeah?
Can you come again on that?
Sorry?
Can you come again on that?
Yeah. So what we're saying is, okay, let me come here. So what we said is we split our data into X train, Y train, X test, and Y test. Right, and then we said we dedicated 80% for training and 20% for testing. So if we just do this, right, what that means is we built our model entirely blind by training, right? And then right at the end of training, we then test it, right? We then test it. But another good way of checking that our model is actually performing well at every training step, we can then subdivide the training set into, we take a certain percentage of this, let's say we take a 20%. Then we can take this 20% and we call it a validation. Validation set, which we use for what? For validating our model. Right? So what that means is at every epoch, right? So epoch number 1, we check y hat minus y, right? And then we validate to see how well it is performing. And then we check y hat minus y. And we are not using y test, we are using y validation. Y validation, right? Is this clear? Right? So what we're doing is we are then improving how we test our model, right? So what that actually means is we can rely on the accuracy that we get after training, because we would have validated our model during training. Yes? Yes, guys, that's clear, yeah? Does that answer your question?
Yeah, it now makes sense.
Come on, guys, is this clear?
Yes, it's clear, Doc, but I have a
it's clear,
question.
Doc.
Maybe I need
Sorry?
clarity.
Yeah, please ask what you need clarity on.
Okay, after validating our model, is there any need to carry out the test at the end of the model?
Yes, you still need to test your model, because you want to see. Because remember, with the training is on seen data, right? And the testing is on unseen data, right? So you still want to, at the end of training, how well is your learning rule when you put in F test, right? And then you get the predictive value of y, how that compares to y hat minus y test, right? So this case is you are now testing on unseen data. And in the validation, we are validating on seen data, right? Is that making sense? Hello?
Yeah.
Guys, you're not responding. Is that making sense?
Yes, it is, Doc.
Yes, it is, Doc.
Yeah, all right. So let's so we now understand what this means, right? So I just want to change the number of epochs because if I specify too many, it means my model will take very long to run, right? And we don't want to spend the whole day running a model. So let me just change that to 500. So in yours as well, change that to 100 instead of 500. Change it to 100. I've changed mine. Otherwise, we'll spend the whole day running the model, right? So the reason why I've said history is I want to plot the history of its training process. I want to be able to visualize its training process. That's all I mean. So when I run this, it will then start training. You say epoch 101, you see it started training. There you go. So you see the accuracy starts off at 0 point and it starts improving, yeah? Can you see this? Yeah?
Yes, Doc.
Yeah, can you see the accuracy is improving, isn't it?
Mm-hmm.
Can you see now? So what that means is I've got, since I'm validating my model, I've got the validation accuracy, I've got the loss and the validation loss. Yeah, I've got the validation accuracy, the loss as well at every step. So what I can actually do is, if I plot to visualize the loss and validation loss, the two, they must go hand in hand, right? Yeah?
Mm-hmm. Yes, Doc.
Yeah, then if I plot the model accuracy, right, the history of the accuracy and the validation accuracy, the two must go hand in hand, right? They must almost follow each other. Yes?
Yes, Doc.
Yeah, so you can see in this instance, I'm using plt.plot and then history from the history that I've defined here, right? This is history of all of this output, the history of this output. Take the loss from the history, also plot the validation loss, right? You can see this, it's taking this validation loss, and that's the loss. So it then takes these values, right? And then this is the accuracy, and then the validation accuracy, right? So you can see I now plotting the loss and validation loss, right? And then I'm plotting the accuracy and the validation accuracy, right? And then what I'll then do is, and remember when we said when we build our model, the next step is to what? Is to evaluate the model. So by model evaluation, we then take X test and Y test, and we want to see how well that is performing. So then, therefore, it will then give us the accuracy rate of the X so which is equivalent to this, right? To say Fx of t, right? The learning rule, and we use Fx test, right? So you can also evaluate how well it, and then what we can then do is we can then say y hat is equal to model.predict classes. We want to predict all the classes, right? And then from there, you'll see it, we'll then get all the predicted classes of y hat. C is equal 0, 0, 1, 0, and so on. Yeah, and then those are what we compare with Y test, right? Is that clear?
Yeah, Doc.
Yeah. So after that, what we then do is you did the performance matrix, right? So in the performance matrix, you guys, you did a confusion.
Sorry, Doc.
Yes.
Sorry, Doc. Can you pop the codes to the chat box? Yes.
Okay. All right. Let me do this. Copy. Okay. We'll see how we interpret these figures, right? Right. Okay. Okay. So when we evaluate our model, so let's do this. So then if we put Y train, let's train Y train. You will see this will give us the last accuracy that we got. This one, 0.8, right? So if we come up here, right, you will see that the average accuracy of our model is about 0.8, right? Right. So if you can see 0.8, so the average, right? So if we evaluate, so if we take for our training process, the average accuracy is 0.8. Yes?
Mm-hmm.
And then for our test, it's 0.78, which is on unseen data. So when you have something, when you've got a model where you get the performance on unseen data is the same on training data, it means it's a very good model. Yeah? That's obvious, isn't it?
Yes, Doc.
Yeah. Yeah?
Can you come again, say?
So if we have, if I come back here, so when we have, when we train our model, isn't it? We are training it on known values, right? And then when we test it, we are testing it on unseen values, right? So if we evaluate our model, right? So if we evaluate our model, if we evaluate our model and we see that the accuracy of our training, right, of the accuracy, right, of our training compared to our testing, right? Right? So this is what we call, so this is a Y hat, and this is a Y. So the difference, if the difference is very small, is very, very small. So what that simply means that our model is able to do well on unseen data, almost the same as on the seen data. So what that means is our learning room has learned the representation of the data. Yeah, is that clear? So what this simply means is we've got a very good working model. So what we can then do is we can you've seen this, we can now do a performance matrix report or classification report. So you know what a confusion matrix is, right? You did that with Dawn. So what we can then do is we can then say from sklearn.matrix import confusion matrix, from sklearn.matrix import classification report, from sklearn.matrix import accuracy score. And then what we then do is we then remember we did model.predict classes. Model.predict classes is the same as doing this, is to say f of x test equal to y hat, right? So which is this? So because we're now predicting our x test so that we see how accurate it gives us y. Then what we then do is we then compare y test and y hat, right? Or y hat and y test. And then we then do a classification report on y test and y hat and see what we get. So you can see from this, we get our precision, our recall, our F1 score, and our support, right? Then you can then see the accuracy. The average accuracy was 0.8 or 0.79 or 0.8. And then you can see our precision, our recall, right? And our F1 score. So remember what precision is, you remember what recall is, and you remember what F1 score is, right? So what that means is we actually have a very good model that we've created. And remember, this is actually from real data. So I think one of the questions was, are we going to be able to apply this on real data, right? And there you go. We actually applied it on real data that we got from yeah? Are there any questions on this, guys?
Yeah, we're good. Sorry, Doc.
Yes.
I've seen we
Yes, sorry. Hello? I can't hear you. Guys, can you hear me?
Yes,
Yes,
Doc.
Yes, we can hear you, Doc.
Yeah, is this clear? Can you see how effortless it is to build a model, right? That's it. Shut up, Peter. So in the next examples, you guys should be able to create my models, and you've understood what this means, right? Clearly understood what that means, and you've clearly understood what this means, right? And you've understood what this means, right? And then even the output to say at every epoch, right? Right? You see 1 hour of 100. You understand what batch size is. You understand what validation split is, right? That you've understood, and then we went to then plot the output of the history of the training process, right? So we want to see the loss and validation loss, and then we want to see the accuracy and validation accuracy, and then we evaluate our model, right? Yeah.
Hello.
Yeah.
Maybe you could repeat on the epochs validation and a little bit up. Right there, where you say history, then we're fitting the model, X train, Y train, epochs 100, batch size 20. and the
Yeah,
validation split is 0.2. What is happening there?
Yeah. So remember. So I want you to then respond. So when we're training our model, what do we need?
Okay. So
Training data.
We need our training data, which is what?
80%.
Yes, which is X train and Y train. Is that clear?
Yes.
Right? And therefore, we also need to specify the number of iterations or the number of epochs. Remember when we did gradient descent, we explained what epoch is, right?
Yes.
It's the number of iterations that you go through. So we said we want to do 100 iterations through our data. And
yes.
Right? And therefore, we're specifying the number of epochs, the number of iterations that we do going through the data, right?
Mm-hmm.
For the training process. Yeah?
Yes.
And remember, we specified what batch size is, right? And we went into great length that we specify a batch size because we don't want our model to be trapped in the local minima. We want it to converge so that it will always give you the global minima.
Oh,
right? That's,
yeah. Now I get it.
Yeah?
Yes.
Yeah, and then the validation split, I just explained what we mean by validation split. By validation split, it means that at every step, instead of waiting right at the end to see how well our model is performing, we take some part of the data, and then at every step of training, we are now validating to see our y hat minus y validation, so that we see how well our model is performing at every step of the training, instead of waiting right at the end. Yeah? So in this instance, we can see that our loss is 0.65, and then our accuracy and our validation accuracy are almost the same.
Yes.
Yeah, and then you can see that the accuracy is increasing as the validation accuracy is also increasing. Yes. So it means our model is performing well, and our loss has to decrease, isn't it? And our loss function is decreasing as you can see that it's decreasing as the number of iterations that we have, because we need our loss, right, to converge to almost where it is 0, right? So that's the point where dy over, we say that's where the point where dl over de is 0. Yeah, is that making sense now? This?
Yes, it is.
Right, and this is not an issue. Yes.
So sorry, Doc. So on the iterations, we reduced from 500 to 100. So was 500 going to give us better accuracy or what?
Yes, it was going to, because more iteration will give you more accuracy. But obviously, it means it was going to take 5 times more, 5 times longer. Okay. Right? I just wanted to cut the time. For some of you, you don't have a Core i9 with 32 gig RAM like me. Right? So therefore, I have to reduce, so that it also permission, run out. Otherwise, some of you know, a blue screen of death if I don't go offend.
Sorry, Doc. Is it possible that you run the same code on different machines, but you get the same data and you get different results, slightly different results?
Yes, of course. Why would you get slightly different results? Can someone explain that? Remember here, guys, that's very easy to explain. Okay. So if I take a set, so let's talk about this. Can I do a set of cards, right? are the order the same, right? If I take that set of cards and I give them to Eve, ndopa mamwe to Farai, ndopa mamwe to Simon, ndopa mamwe to Dr. Jones, right? Are we all going to get the same result? Yes or no?
Not possible.
No.
Yeah, there you go. That
Not at
answers.
all.
Right? So therefore, if we want to get, I'll show you then how to get the same result by what we call
No,
seeding.
definitely no.
Yeah. So you understand, right? Why it will be slightly different. Slightly different.
Yeah, yes, I get it.
You get it, yeah? Yeah, so there you go, guys. Matter building models, what you see. So if you understand the theory, building models is effortless. Right? So now, yes.
Sorry for my so many questions. As a layman, someone from an econometric background, I used to know probably when you're probably creating a line of best fit, you come up with an equation, right? Then probably you have the actual equation of that line, right? To actually say you have the inputs probably X that you want to fit into that equation, then to actually try to predict or try to estimate what would be the value of Y B given the actual input parameters. So in this case, we have managed to train the model. We have managed to test the model and see its accuracy. So given probably now we have a new data set of the input variables, can we actually be able to now say, okay, we now have these all these 8 input parameters. What would be the class given those input space? How then we will be able to tackle such a scenario?
Yeah, but your question is already answered, right? Okay. So in this instance, right, we want our, so when we want to predict, right? So when we want to predict, since we've created our model, if we want to predict, we say model.predict, right? And then it gives, then we input into that our unseen data, isn't it?
Okay.
Yes?
All right.
Yeah, is that clear? We input our what? Our unseen data, which is X test, isn't it?
I see.
Yeah? Remember, here I said model.predict, meaning I want you to predict the classes that will be predicted by inputting our data, unseen data X test. And here I'm just calling it Y hat. So if I've got some values, I just say model.predict classes, and then I specify those 8 values, and then it should give me one output. But in this case, my X test, it comprises of 154 values, and it will then assign those and give me this output here, right, of 0, 0, 1, and so on, right? That's the same. Yes?
Yeah, it's now clear.
It's clear, yes? Yeah? And then here you did my performance machine learning performance matrix, right? And we said kune precision, recall, F1 score, accuracy, right? And then there's receiver operating characteristic or area under curve, right? And in this instance, we turn precision, recall, support or sensitivity, right? And therefore we've got our results here for for 0 and 1, which is meant for no diabetes, and 1 for diabetes. What is the precision? What is the recall? Right? What is the precision? What is the recall? Right? And what is the F1 score? What is the accuracy? Right? So there you go. That's it. Zvatopera. What else do you want? Even the data developer model, zvatopera. So if you are doing any project, this was not it, but it was this. Right? Maybe we might do some more exploratory data analysis, but that's it. Can you see? Because you guys are so surprised how easy it is because of the theory, so that you are able to understand this whole process. Right? You're so surprised. You're expecting to see thunder and lightning.
Doc, we are actually surprised how this is so. Now it seems so easy when we do it like this. But the question, the question that is on most of our minds is, after we have developed such a model, okay, what is the essence of these results that we are looking at? For example, if we say the precision 0.75, let's say now I want to put it back into the community to then say my model is doing A, B, C, D, and this is actually what.
Absolutely. So this model that we've developed, this simple model, right? A simple model that we've developed. Can you see how accurate it is, right? Yeah. So this simple model that we've developed, an accuracy rate of 80%. That means our model is performing well, right? And then if you look at the precision, right? How precise the model is. This is actually better than your COVID-19 test. Huh? So the model is a good model. So what that actually means, right? What does that actually mean, right? Remember, demarcated performance metrics. What do we mean by precision? What do we mean by support or sensitivity, right? What do we mean by that? Yeah? What do we mean by accuracy? Yes? Come on, guys. Demarcated performance.
Maybe to just try, Doc. Our accuracy, if it is this high, it means that my false false negatives, the chances of getting into that trap are very slim. Could you
Absolutely, right? So what that means is to develop a very good model, right? On our first attempt, and remember, 30 hyperparameter tuning, you can always tweak these parameters to get a better performing model. We're saying this is our first iteration of building the model. To just render, document later how you tweak these so that you increase the performance of the model, right?
Just hello.
Yes, guys.
Yeah, he's saying we are in a text of a community.
Sorry?
I want to interpret things. He's saying now we want to interpret in the community context where we're saying our model is doing 1, 2, 3, 4, 5, and as it is got a precision of 80%, which means it is doing so. We want to be able to explain our model to a layman's person. How big can we do it given the data set that we have built a model like
yeah, okay.
one?
So what that simply means, right? If we go back, Kuno, right? So it means that so now when we're now testing the model, right? So what that actually means is we can go out into the community. We've created our model and seen that it works well on unseen data. So what that means is we only take these 8 features or variables to be able to predict the class, right? We do not need to wait for my results A class. So our model will be able to 80% of the time give us an accurate value, A class, and which that class meaning to say someone is diabetic or not, right?
Okay. Yeah. Right now, I'm quite happy that you are answering my initial question. So, right, let's say I have my Sekuru who is in Dante, and I've seen that this model is 80% correct in predicting either if he is diabetic or not. And then I get those features 1 to 8. How do I come back and then put them back into this model to then say I have a classification basing on the 8 data points that he might have provided me with?
Oh, okay. So when we want to, okay. So let's go back here, right? So let's assume that I know my data points actually right? Yeah. So let's come back here. Where we've scaled our data, right? So what we do is we take these 8 data points, right? So let's do this, right? So what that means is for your Sekuru now, unotora those 8 data points, right? That total those 8 data points, not my x is equal to, right? This array, isn't it? Right? Yeah?
Yes, following.
Yeah? Not my x is equal to this array. It's not showing me all these values. 1, 2, 3, 4, 5, 6. Let's just add 0.66. All right, 1, 2, 3, 4, 5, 6, 7. Let's add another one. 0.543. So now we have so let's just call this Sekuru. Yeah?
Yes.
So it means for my Sekuru I would have captured the 8 values, right?
Yes.
Oh, okay. So np dot array. Yeah?
Mm-hmm. Yes.
Then what I then do, the end of Panashe model dot predict classes, right? The Panashe Sekuru. Yeah?
Yes.
Yeah? And if I run, yeah, and if I run that, it should give me a result, isn't it? I'm trying to find out what the error is. User code, what the shape is complaining about the shape. I think I just need to change the let me compare that with my X test and let me see what's the difference. X test. All right, so let me look at my X test. All right, X test is called double. All right, so I need to say that my Sekuru, no, but it's a double like this. That the structure is the same. Run this, right? And now I can now run it. You see? Now that's the output. Yes.
Yes.
Yeah. So what that means is giving me a class of what?
0.
Meaning your Sekur is not what?
Diabetic.
Not diabetic.
Yeah, there you go. So what else do you want?
I
think you guys, you're seeing how too simple it is, Marcus Shamisika, because you're expecting some thunder and lightning and hard manual labor and kugomera neku and then
So the dictionary
maybe Chasarapa Futi Doku is to probably find another example where there are other operations that is not quit up, like 1 or 10 coding. So
exactly. So but remember, it's one step at a time, guys. But at least with this, you simply remember I was telling you developing models should be effortless.
Yes, it is. It is.
Yeah, I'm not going to be effortless. So, ukona wako gomera pane yeah. Oh, okay, guys. So let me upload this notebook so that you can have a look at it and play around with it. But now, question all the code, right? You see how simple it is, and then tomorrow. Takuko build my models, my exercises, real life data, maker. Then you realize,
sorry.
Maybe this question is for tomorrow, Doc, but probably we have managed to build this model, and we have managed to see that these 8 features are actually statistically significant in terms of predicting our class. Probably I want to take these variables to a layman's point of view. Probably I want to actually say to build a credit scoring model, right? To say I now have this, instead of using this particular deep learning model, I now want just to use simple credit scoring model, whereby the inputs in terms of weighting, I just take them from this model.
Yeah, remember, Kotika, in a deep learning model, remember, when we're doing back propagation, assign my weights, right? Remember?
Yes.
It assigns weights, right? And my variables or features that do not contribute to the predictive power of the model are assigned smaller weights. Already, it means that your model has got all your weights already built into it. All you just need to do is say model.predict classes, canarima classes. Pera, the weights already, it knows already the weights from the training process because of back propagation. Pera. Then you this do the classical way of doing it. The model will do it for you.
Is there
what you're interested in is the output order from the model, right? Because you can also do a model dot tab weights, right? And then to show you my weights actually. Yeah, there you go. Don't my weights actually. That is very good. Yeah. But I didn't know model. Just because with Achinakua printer doesn't mean they're not there. Right? Remember here we've got 8 input features and 20 neurons pending Rikini. Yeah? Yes. Be able to give us this weights. Right? So therefore it's actually applying those weights to be able to do the model predict. Yeah? So I think you guys got
sorry, Doc. Is there maybe a recommended number of data points if I want to on building the model?
So we'll look at cases where you've got a very small data set. What can you do to trick the model as if you've got a huge data set, right? So we'll look at all those techniques, right? We'll, it's a K-fold cross-validation, right? Yeah?
Okay.
This is what said. So normally, what you can actually do with everything that you've learned to show you that how effortless it is.
Yeah,
so
thank you, Doc.
Yeah, so let me upload this notebook, right? And then you can now, that 18 past 9, you guys are too excited today. That 18 past 9. And then tomorrow to continue, and tomorrow we've got the whole day, right? Tomorrow continue going with them examples like I wonder with real life data from all those different sites, right? I showed you that you can actually Google and my data sets, isn't it? And don't go to the data that you know data. You can just use that data. Just exactly using this one, and then we'll actually then go into detail the hyperparameter tuning in it was saying all of those other things. But this first time round was actually showing building a model after everything we've gone through is effortless. Right? That's the whole point. If you understand all of that, you shouldn't struggle building a model. Okay, guys, let me upload this model. Some of you are so excited. I'm tired of Okay, guys, that's enough for today. Swakwana, guys, Swakwana. Right? We can all agree. We can stop. You can stop here, right?
Thank you. Thank you.
Yeah. Okay, guys.
Thank you, Doc.
Swakwana.
Thank you, Doc.
All right. Cheers.